Hello, and welcome. I'm your night librarian. So glad you're here tonight. I hope you don't mind. I've put on some relaxing music for you. It should begin shortly, softly in the background. Let's take a moment to slow down together. There's nothing you need to do, and nowhere you need to be. Let's light up the candle. Just a small, warm glow, steady and comforting. Take a gentle breath in and let it go. Tonight, we'll be talking about something simple, something calm, something that you can drift in and out of as you rest. You don't need to stay awake. Just listen, relax, and allow yourself to fall asleep whenever you're ready. This library grows with its travelers. If these stories help you rest, subscribing helps us grow and guides other sleepless souls here. A like or a quiet comment is always appreciated. But for now, all you need to do is relax. The library is quiet. The candle is lit. Settle in. Get comfortable. And allow your eyes to grow heavy. Welcome back to our restricted section of the archives, a multi-volume catalog of our home galaxy. Tonight, we'll explore our local neighborhood in the Milky Way galaxy. We'll talk about our sun, the stars nearby, and the arm of the galaxy where we live. There's no need to remember every detail. Just let the words wash over you, like gentle waves on a shore. Take a deep breath, get comfortable, and let's begin our slow drift through the cosmos. Our sun, a medium star. Let's start with something familiar. Our sun, the bright ball of light that warms our days. You've seen it thousands of times, but have you ever really thought about what it is? The sun is a star, just a star, not a special one. Really, it's what astronomers call a yellow dwarf. Medium-sized, middle-aged, ordinary in almost every way. And yet, it's everything to us. The sun is about 4.6 billion years old. Imagine that. 4,600 million years. It was born from a cloud of gas and dust, spinning and collapsing, getting hotter and hotter until nuclear fusion began at its core. At the center of the sun, hydrogen atoms are crushed together to make helium. This process releases energy, enormous amounts of energy. That energy slowly works its way out from the core, taking thousands of years to reach the surface. Then it flies through space as light, reaching Earth in just 8 minutes. The sun is large, very large. You could fit about 1 million Earths inside it. But in the grand scale of stars, it's quite average. There are stars hundreds of times bigger, and stars much smaller too. Every second, the sun converts about 4 million tons of matter into pure energy. 4 million tons. Every single second. It's been doing this for billions of years, and it will keep doing it for billions more. The sun doesn't burn like a fire burns. There's no oxygen in space. Instead, it's a continuous nuclear reaction, held together by its own gravity. It's a careful balance. Gravity trying to crush everything inward. Nuclear fusion pushing everything outward. These two forces in perfect balance create our steady, reliable sun. The sun's layers. The sun has layers, like an onion. At the very center is the core, where fusion happens. The temperature there is about 15 million degrees Celsius. 15 million. It's almost impossible to imagine such heat. Around the core is the radiative zone. Here, energy bounces around for thousands of years, slowly making its way outward. Light particles called photons are constantly absorbed and re-emitted, moving just a tiny bit further out each time. Then comes the convective zone. Here, hot plasma rises like boiling water, reaches the surface, cools, and sinks back down. This churning motion brings the energy closer to the surface. The surface we see is called the photosphere. This is where light finally escapes into space. The temperature here is about 5,500 degrees Celsius. Still incredibly hot, but much cooler than the core. Above the photosphere is the chromosphere, a thin layer of gas. And beyond that is the corona, the sun's atmosphere. Strangely, the corona is hotter than the surface. Much hotter, sometimes millions of degrees. Scientists are still working to understand why. The sun also has a magnetic field. This field creates sunspots, dark patches on the surface that are slightly cooler. The magnetic field also causes solar flares and coronal mass ejections, sending particles streaming into space. The sun's future. The sun is middle-aged. It has about 5 billion years left. 5 billion years of steady burning. But eventually, the hydrogen in the core will run out. When that happens, the sun will begin to change. It will grow larger, much larger, becoming what's called a red giant. It will expand past Mercury's orbit, past Venus. It might even reach Earth. But don't worry, this won't happen for a very, very long time. After the red giant phase, the sun will shed its outer layers, creating a colorful cloud called a planetary nebula. The core will remain, a small, dense object called a white dwarf, about the size of Earth but incredibly heavy. A single teaspoon of white dwarf material would weigh tons. The white dwarf will slowly cool over trillions of years, eventually becoming a cold, dark cinder. But again, this is so far in the future it's hard to truly grasp. The Orion Arm. Now let's zoom out. Let's look at where the sun lives in our galaxy. The Milky Way is a spiral galaxy. It has long arms that curve out from the center, like a pinwheel. Our sun lives in one of these arms. It's called the Orion Arm, or sometimes the Orion Spur. The Orion Arm is not one of the major arms of the galaxy. It's smaller, a spur that connects two larger arms. The Perseus arm and the Sagittarius arm. Think of it as a branch between two main limbs. Our sun sits about 26,000 light-years from the center of the galaxy. 26,000 light-years. That means if you could travel at the speed of light, it would take 26,000 years to reach the galactic center, way out in the suburbs of the galaxy, far from the crowded center. The Orion Arm is named after the constellation Orion. When we look toward the constellation Orion in the night sky, we're looking along our local arm of the galaxy. We're looking at stars that are our neighbors. The arm stretches for thousands of light years. It contains billions of stars, young stars, old stars, giant stars, tiny stars, stars being born in clouds of gas, stars dying in brilliant explosions. Our Sun orbits around the center of the Milky Way, just like Earth orbits around the Sun. But this orbit is much slower. It takes about 225 million years for the Sun to make one complete trip around the galaxy. The last time the Sun was in this exact position, dinosaurs were just beginning to walk the Earth. As we drift along in our orbit, we move through the Orion Arm, surrounded by our stellar neighbors. Some are close, some are farther away, but all are part of our local neighborhood. Our small corner of this vast, turning spiral of stars. And that's where we'll continue our journey next, to the nearby stars, our closest neighbors in the cosmic sea. But for now, just rest. Float in the gentle knowing that you are here, in this arm, in this galaxy, part of something ancient and enormous and beautiful. Our nearest neighbors. Let's drift closer to home now. Let's visit the stars nearest to our Sun, the stars that are practically next door. In cosmic terms, space is vast, unimaginably vast. The distances between stars are so large that we measure them in light years. A light year is the distance light travels in 1 year. Light moves fast, very fast, about 300,000 kilometers per second. In 1 year, it covers about 9.5 trillion kilometers. The nearest star to our Sun is called Proxima Centauri. Proxima means nearest in Latin. It's about 4.24 light years away. That sounds close, doesn't it? But think about what it means. If you could travel at the speed of light, it would still take more than 4 years to get there. Proxima Centauri is a red dwarf star. Red dwarfs are the most common type of star in the galaxy. They are small, much smaller than our Sun. Proxima is only about 1/7 the size of the Sun, and it's much dimmer, much cooler. Its surface temperature is only about 3,000 degrees Celsius, compared to the Sun's 5,500 degrees. Red dwarfs burn their fuel very slowly. This means they live for a very long time, trillions of years. Proxima Centauri is already about 5 billion years old, the same age as our Sun. But while our Sun will die in another 5 billion years, Proxima will keep burning for thousands of billions of years more. The Alpha Centauri system. Proxima Centauri is not alone. It's part of a triple star system called Alpha Centauri. The other two stars are Alpha Centauri A and Alpha Centauri B. These two stars are closer to us than Proxima, but only slightly. They are about 4.37 light years away, just a tiny bit farther. They orbit each other, locked in a cosmic dance. Two stars spinning around their shared center of gravity. Alpha Centauri A is very similar to our Sun, almost like a twin. It's just slightly bigger and slightly brighter. If you lived on a planet orbiting Alpha Centauri A, you would see a Sun very much like ours. Warm, yellow, familiar. Alpha Centauri B is a bit smaller, an orange dwarf, still similar to our Sun, but cooler and dimmer. Together, these two stars orbit each other every 80 years. Sometimes they're close together, sometimes they're farther apart, but always they dance. Proxima Centauri orbits far from these two stars. So far that it takes hundreds of thousands of years to complete one orbit. Some astronomers aren't even sure if Proxima is truly bound to the other two, or if it's just passing by. But for now, we consider them one system. 3 stars, our nearest neighbors, planets around Proxima. In recent years, scientists have discovered planets orbiting Proxima Centauri. At least 2 planets, maybe more. One planet, called Proxima Centauri b, orbits in what's called the habitable zone. This is the region around a star where temperatures might allow liquid water to exist. Liquid water, the key ingredient for life as we know it. Proxima b is slightly larger than Earth. It completes one orbit every 11 days. 11 days. Imagine living on a world where a year is only 11 days long. But life on Proxima b would not be easy. The planet is very close to its star, much closer than Earth is to the Sun. It's probably tidally locked, meaning one side always faces the star, baking in eternal daylight, while the other side freezes in eternal darkness. And Proxima Centauri is an active star. It produces powerful flares, bursts of radiation that could strip away a planet's atmosphere. Any life on Proxima b would need to be tough. Very tough. Still, it's exciting. A potentially habitable planet, right next door in cosmic terms. It reminds us that planets are everywhere, orbiting stars throughout the galaxy. Some like Earth, some very different. Barnard's star. Let's move to another neighbor. Barnard's star. This star is a bit farther away, about 6 light years from us. It's named after E. Barnard, an astronomer who noticed something special about it in 1916. Barnard's star moves fast, very fast across the sky. It has the largest proper motion of any star we can see. Proper motion means how much a star appears to move against the background of more distant stars. Most stars move so slowly that you'd never notice in a human lifetime. But Barnard's star moves noticeably in just a few years. It's moving toward us. Well, not directly toward us, but in our general direction. In about 10,000 years, it will be the closest star to our Sun, passing within just 4 light years. Then it will continue on, drifting away again. Barnard's star is another red dwarf, small and dim. You can't see it without a telescope. Even though it's relatively close, it's just too faint for the naked eye. For many years, astronomers thought there might be planets around Barnard's star. There were hints in the data, tiny wobbles that suggested something pulling on the star, but the evidence was never strong enough. We still don't know for certain if it has planets. The search continues. Vol.2 and Librarian 21185. There are other neighbors too. Vol.2, about 7.9 light years away. Another red dwarf, faint and small. It became a bit famous in science fiction. In Star Trek, there was a famous battle at Vol.2, but in reality, it's just a quiet little star. Librarian 21185 is about 8.3 light years away. Also a red dwarf. Are you noticing a pattern? Most of our nearest neighbors are red dwarfs. This makes sense. Red dwarfs are the most common stars. They outnumber all other types combined. Librarian 21185 was once thought to have planets. Astronomers saw wobbles in its motion, but later observations showed these wobbles might be caused by the star's own activity, not by planets. Space is tricky. It's easy to see patterns that aren't really there. Sirius, the brightest star. Now let's talk about a star you've definitely seen. Sirius, the brightest star in our night sky. It's in the constellation Canis Major, the big dog. That's why it's sometimes called the dog star. Sirius is about 8.6 light years away. That makes it one of our nearest neighbors. But that's not why it's so bright. It's bright because it's a big star, much bigger and much hotter than our sun. Sirius is actually two stars, Sirius A and Sirius B. Sirius A is the bright one. It's about twice as massive as our sun and 25 times more luminous. It's a white star, hot and brilliant. Sirius B is the hidden companion. It's a white dwarf, a dead star, the collapsed core of what was once a normal star. Long ago, Sirius B was probably bigger than Sirius A, but it burned through its fuel faster and died, leaving behind this small, dense remnant. White dwarfs are strange objects. They are about the size of Earth but contain as much mass as the Sun. The matter is compressed so tightly that a single teaspoon would weigh tons. The gravity is intense. The two stars orbit each other every 50 years. When Sirius B passes in front of Sirius A, as seen from Earth, the brightness of the system changes ever so slightly. Ancient astronomers knew Sirius well. They tracked its movements. They wove it into their myths and calendars. And that brings us to a gentle pause. We visited our nearest neighbors, small red dwarfs and bright giants, stars with planets and stars alone, each one a sun, each one a world unto itself. Rest now in the knowledge of these distant lights, these islands in the dark. We'll continue our journey soon, drifting further through our local neighborhood, meeting more stars, learning more stories. But for now, just breathe, just float, just be. The local bubble. Let's pull back now. Let's look at an even larger neighborhood, a region of space called the local bubble. Imagine the space between stars. You might think it's completely empty, a perfect vacuum, but it's not. Space is filled with gas, very thin gas, just a few atoms per cubic centimeter. But it's there. Hydrogen mostly, some helium, traces of other elements. In some regions, this gas is thicker, denser. These are called molecular clouds, dark nebulae, places where new stars are born. In other regions, the gas is thinner, much thinner. These are called bubbles. Our sun sits inside one of these bubbles. The local bubble. It's a region about 1,000 light years across where the gas is very thin, only about 1/10 as dense as the average space around it. Why is there a bubble? Scientists believe it was created by supernovae, exploding stars. When a massive star dies, it explodes with tremendous force. The blast wave pushes gas outward, creating an expanding shell. Several supernovae, exploding over millions of years, carved out this cavity. The walls of the bubble are denser, the gas that was pushed outward. These walls glow faintly. You can't see them with your eyes, but telescopes can detect them. They are warm, heated by the ancient explosions that created the bubble. Our sun is moving through the local bubble. We're not at the center. We're slightly off to one side. In a few million years, We'll reach the edge and pass into denser regions of space. But for now, we float in this cleared zone. This gift from long-dead stars, the Gould Belt. Within the local bubble, there's another structure, the Gould Belt. It's a ring of stars and gas clouds. Young stars mostly. Hot, bright stars that were born only a few million years ago. The Gould Belt is tilted compared to the main disk of the Milky Way. It's at an angle, like a ring worn slightly crooked. This belt includes some famous nebulae, places where stars are being born right now. The Orion Nebula is part of the Gould Belt. On a clear night, if you look at the constellation Orion, you can see it, a fuzzy patch in the sword that hangs from Orion's belt. Through a telescope, it's breathtaking, a glowing cloud of gas, pink and red and purple, with young stars blazing at its heart. The Orion Nebula is a stellar nursery. Inside that cloud, gravity is pulling gas together. Clumps are forming, getting denser, getting hotter. Some will become stars. Some already have. Young stars that just turned on their fusion engines in the last few million years. There are other nurseries in the Gould Belt too. The Taurus Molecular Cloud, the Rho-Ophiuchi Cloud Complex, all places where stars are being born, all relatively close to us, within a few hundred light years. Why is the Gould Belt tilted? Why does it exist at all? Astronomers aren't entirely sure. Maybe it was triggered by a collision with a dwarf galaxy long ago. Maybe by a powerful supernova. Or maybe it's just a natural ripple in the disk of the Milky Way. The galaxy is not smooth. It has structures, waves, currents in the stellar sea, red giants among us. Not all nearby stars are small and dim. Some are giants, stars in the late stages of their lives, swollen and bright. Take Arcturus, for example. It's about 37 light years away. A red giant, much larger than our sun, about 25 times wider. If you placed Arcturus where the sun is, it would stretch almost to Mercury's orbit. Arcturus is orange-red, cool for a star, only about 4,300 degrees Celsius at the surface. But because it's so large, it's very bright, about 170 times more luminous than our sun. Arcturus is moving fast through space. It's passing through our neighborhood. In about 500,000 years, it will be farther away. Eventually, it will leave this part of the galaxy entirely. It's a visitor, a traveler. Then there's Aldebaran, the Eye of Taurus the Bull, about 65 light years away. Another red giant, even bigger than Arcturus, about 44 times the diameter of the sun. Aldebaran has already burned through the hydrogen in its core. Now it's burning helium. This is a later stage in a star's life. Eventually, Aldebaran will shed its outer layers and become a white dwarf. But not yet. For now, it shines bright and orange in our sky. These red giants remind us that stars have life cycles. They are born, they live, they change, they die. Our sun will become a red giant one day, but that's billions of years from now. Plenty of time. Binary stars. Many stars are not alone. They have companions, partners, stars orbiting other stars. Scientists estimate that more than half of all stars are in binary or multiple star systems. Two stars orbiting each other. sometimes 3, sometimes even more. Single stars like our Sun might actually be unusual. Some binary stars are close together, so close they can exchange material. Gas from one star flows to the other. These are called close binaries. They can create strange and beautiful phenomena. Other binaries are far apart, separated by thousands or millions of kilometers. They orbit each other slowly, over years or decades or centuries. Alpha Centauri is a binary system, as we mentioned. Sirius is too, and there are many others nearby. Luton 726-8, Groombridge 34, Epsilon Eridani might have a distant companion, though we're not certain. Binary stars are important for astronomy. By watching how they orbit each other, scientists can measure their masses. This helps us understand how stars work, how they form, how they evolve. Living on a planet in a binary system would be strange. Imagine 2 suns in the sky, 2 sunrises, 2 sunsets, or perhaps one sun always overhead while another circles the horizon. Or periods with 2 suns, followed by periods with just one. Science fiction loves binary systems. The planet Tatooine in Star Wars, with its 2 suns. But reality is just as fascinating. There really are planets out there with double sunsets. Worlds we're only beginning to discover. Brown dwarfs, failed stars. Let's talk about something unusual. Brown dwarfs. They're not quite stars, not quite planets, something in between. A brown dwarf forms like a star, from a collapsing cloud of gas. But it doesn't have enough mass to start hydrogen fusion in its core. It's too small. Not enough gravity, not enough pressure. The smallest stars are about 80 times the mass of Jupiter. That's the minimum needed for hydrogen fusion. Brown dwarfs are below this limit, maybe 13 to 80 Jupiter masses. Some brown dwarfs can fuse deuterium. That's a heavy form of hydrogen. This produces some heat, some light, but it doesn't last long. Deuterium runs out quickly. Then the brown dwarf just cools, slowly radiating away its heat. Fading. Brown dwarfs are hard to find. They are dim, very dim. They glow mostly in infrared light. Heat radiation. You need special telescopes to see them. But we found several nearby. Lumen 16 is the closest brown dwarf system to us, about 6.5 light-years away. It's actually 2 brown dwarfs orbiting each other, a binary brown dwarf system. Y0855 is even closer, about 7.2 light-years away. It's one of the coldest brown dwarfs we know, maybe minus 48 degrees Celsius. Cold enough for water clouds to form in its atmosphere. Water clouds. On a failed star, brown dwarfs blur the line between stars and planets. They remind us that nature doesn't always fit into neat categories. The universe is messy, complicated, full of objects that are hard to define. The stars we see, on a dark night, far from city lights, you can see thousands of stars with your eyes alone. About 2,000 to 3,000 stars, depending on how good your eyesight is and how dark the sky is. Most of these stars are within a few hundred light years. Our local neighborhood. Some are closer, some farther, but all are relatively nearby compared to the size of the galaxy. The brightest stars in the sky are not always the closest. Sirius is both close and bright, but Rigel, in Orion, is about 860 light-years away. It looks bright because it's a supergiant, enormously powerful, and many of the closest stars are invisible to our eyes. All those red dwarfs were mentioned: Proxima Centauri, Barnard Star, Wolf 359. You need a telescope to see them. This tells us something important. Our view of the universe is biased. We see the bright things, the powerful things, but most of the universe is dim, quiet, modest. Most stars are red dwarfs, small and faint. Most planets are probably similar. Not dramatic, not spectacular, just ordinary worlds orbiting ordinary stars. But that's beautiful in its own way. The universe doesn't need to be dramatic to be wonderful. The simple fact that stars exist, that planets exist, that atoms can arrange themselves into galaxies and nebulae and, yes, even into living things. That's miracle enough. Let yourself drift now, surrounded by these stars, these points of light, each one a sun, each one burning, each one making its slow circle around the galaxy. You are made of star stuff, atoms forged in ancient stellar furnaces. You are the universe becoming aware of itself. Rest in that knowledge. Rest in that wonder. Just breathe. Just be. The solar wind. Let's return to our sun for a moment. We talked about the light it sends out, the heat, the energy, but the sun sends out something else too. A wind. The solar wind. The sun's outer atmosphere, the corona, is so hot that gravity can't hold it all in place. Particles escape, protons and electrons. Mostly, they stream outward into space at incredible speeds, several hundred kilometers per second. This is the solar wind, an invisible river of charged particles flowing past Earth, past Mars, past Jupiter, all the way to the edge of the solar system and beyond. The solar wind creates a bubble around our solar system. We call it the heliosphere. Inside this bubble, the solar wind dominates. Outside, in interstellar space, the wind from other stars takes over. Earth is a magnetic field. This field protects us from the solar wind. When the charged particles hit our magnetic field, they're deflected, pushed aside. Most of them flow around Earth like water around a stone in a stream. But some particles get trapped in the magnetic field. They spiral along the field lines toward the poles. When they hit Earth's upper atmosphere, they collide with atoms of nitrogen and oxygen. These collisions create light, beautiful, shimmering light, the aurora, the northern lights and southern lights, green curtains of light dancing across the sky, sometimes red, sometimes purple. The aurora is the solar wind made visible. It's a reminder that our sun is always reaching out, always touching us. The solar wind varies. Sometimes it's calm, sometimes it's strong. When the sun releases a coronal mass ejection, a burst of plasma, the solar wind becomes a storm. These storms can interfere with satellites, with power grids, with radio communications. But mostly, the solar wind is gentle. A steady breeze from our star, pushing back against the interstellar medium, creating our little bubble of home. Interstellar space. Beyond the heliosphere lies interstellar space, the space between stars. It's not empty. We mention the gas, but there's also dust. Interstellar dust grains are tiny, much smaller than a grain of sand, maybe a millionth of a meter across. They are made of carbon and silicates, elements cooked inside stars and blown out into space. These dust grains drift through the galaxy. Sometimes they gather in clouds, dark nebulae that block starlight. You can see these dark patches in the Milky Way on a clear night, regions where no stars shine through, not because there are no stars there, but because dust blocks them. Dust might seem like a nuisance. It blocks our view, but dust is essential. Stars form in dusty clouds. Planets form from dust. The earth beneath you, the air you breathe, your own body, all made from dust that once drifted between the stars. Interstellar space also contains cosmic rays. These are high-energy particles, protons mostly, traveling at nearly the speed of light. They come from supernovae, from pulsars, from other violent events in the galaxy. Cosmic rays zip through space, through Earth, through you, right now. Cosmic rays are passing through your body, thousands every second. Most do nothing. They pass right through, but occasionally one hits an atom in your cells. This can cause mutations. It's one reason why space travel is dangerous. But cosmic rays are also fascinating. They are messengers from distant events. By studying them, we learn about the galaxy, about black holes and neutron stars, about the most extreme environments in the universe. Rogue planets. Not everything in space orbits a star. Some planets drift alone through the darkness. Rogue planets. Wondrous. How do planets become rogues? Sometimes they are ejected from their solar systems. Gravitational interactions can fling a planet out into space. A close encounter with another planet, or with a passing star. The planet gets a gravitational kick and flies away, never to return. Other rogue planets might form on their own, not around a star, but in the interstellar medium, like brown dwarfs, but even smaller. These objects blur the line between planets and stars even further. How many rogue planets are there? We don't know. They are nearly impossible to see. They don't reflect starlight because they are not near a star. They don't glow with their own light because they are too small and cold. But astronomers have found a few using clever techniques. When a rogue planet passes in front of a more distant star, it acts like a lens. Its gravity bends the starlight. For a few hours or days, the distant star appears brighter. This is called gravitational microlensing. Using this method, scientists have discovered several rogue planets, and they've estimated there might be billions in the Milky Way, maybe more rogue planets than stars. Imagine that. Dark world drifting through the void. Some might be gas giants like Jupiter. Some might be rocky like Earth. Some might even have moons. And those moons might have atmospheres. Perhaps even life. It's a strange thought. Life on a world without a sun. Getting energy from the planet's internal heat instead of starlight. Living in eternal darkness. But the universe is full of strange things. We shouldn't assume we know all the ways life can exist. The speed of stars. Stars move. They orbit the galaxy, but they also move relative to each other. Some stars are approaching us. Some are moving away. We measure this using the Doppler effect. When a star moves toward us, its light gets compressed, shifted toward the blue end of the spectrum. When it moves away, the light gets stretched, shifted toward the red. By measuring these shifts, astronomers can calculate how fast a star is moving and in which direction. Most nearby stars are moving relatively slowly, a few dozen kilometers per second. They are all orbiting the galaxy together, like cars on a highway. Small differences in speed, but generally going the same direction. But occasionally, we find a star moving very fast. A high-velocity star. These are oddballs. They are moving so fast they'll escape the galaxy entirely. One example is US 708. It's a white dwarf moving at about 1,200 kilometers per second. That's fast enough to leave the Milky Way. How did it get going so fast? Astronomers think it was once part of a binary system. Its companion was a white dwarf too. The two stars were spiraling together, getting closer. Eventually they touched, merged, and exploded in a type of supernova. US 708 was flung away by the explosion. There are other high-velocity stars too. Some were accelerated by close encounters with black holes. Some were ejected from the galactic center. Some came from other galaxies entirely, tossed into intergalactic space by gravitational interactions. These runaway stars are rare, but they remind us that the galaxy is dynamic. Things are always moving, always changing. Nothing stays still. Stellar generations. Stars come in generations, not like human generations. These generations span billions of years, but the concept is similar. Older stars, younger stars, and the younger stars are made from the remains of the older ones. The first stars in the universe, born about 13 billion years ago, were made only of hydrogen and helium. Those were the only elements that existed after the Big Bang. These first stars, called population 3 stars, were massive, huge, and short-lived. They burned bright and died quickly, exploding as supernovae. Those explosions created heavier elements: carbon, oxygen, iron, gold, all the elements we see today. The next generation of stars, population 2 stars, formed from gas enriched with these heavier elements. These stars are still around, the oldest ones in our galaxy. They are found mostly in the halo and in globular clusters. Ancient stars orbiting far above and below the galactic disk. Our Sun is a population 1 star, a newer star, made from gas that's been enriched by many generations of supernovae. That's why the Sun, and planets like Earth, contain so many heavy elements. When you look at nearby stars, you're seeing different generations mixed together. Old red dwarfs that have been around for billions of years. Middle-aged stars like the Sun young. Hot stars just a few million years old. Each generation tells a story. The chemical composition of a star reveals its history, where it came from, when it was born, what other stars contributed to its creation. We are the products of countless stellar generations. Every atom in your body, except hydrogen, was made inside a star. Carbon in your cells, calcium in your bones, iron in your blood, all created in stellar furnaces and scattered by supernovae. You are, quite literally, made of stardust, and so is everything around you. The air, the ground, the water, all stardust. The universe recycling itself, creating new forms from old. White dwarfs and their slow fade. We've mentioned white dwarfs a few times. These are the remnants of stars like our sun, the final stage. Let's talk about them more. When a star like the sun runs out of fuel, it swells into a red giant. Then it sheds its outer layers, creating a planetary nebula. What's left is the core, dense, hot, about the size of Earth but with a mass of the sun. This is a white dwarf. It's made mostly of carbon and oxygen. The atoms are packed so tightly that matter behaves strangely. It's held up not by thermal pressure, but by something called electron degeneracy pressure, a quantum mechanical effect. White dwarfs don't burn fuel. They don't have fusion reactions. They just glow with leftover heat, slowly cooling over billions of years. When a white dwarf first forms, it's incredibly hot, maybe 100,000 degrees Celsius. It glows brilliant white. Over time, it cools. After billions of years, it might cool to 10,000 degrees. It turns yellow, then orange, then red. Eventually, after trillions of years, a white dwarf cools completely. It becomes a black dwarf, a cold, dark cinder. But the universe isn't old enough for any black dwarfs to exist yet. Even the oldest white dwarfs are still glowing faintly. Sirius B is a white dwarf. So is Procyon B, the companion to Procyon, another bright star in our sky. These white dwarfs are hard to see because they are so small and their bright companions outshine them. But they are there, quiet reminders of stellar death. One day, billions of years from now, our sun will become a white dwarf. Earth, if it still exists, will orbit a small, fading ember. The oceans will be long gone, the atmosphere stripped away, just a cold rock circling a dying star. But that's so far in the future it's hard to comprehend. For now, the sun shines steady and bright. For now, we're safe in our little corner of the galaxy. Rest in that knowledge. Rest in the present moment. Let go of the distant future. Let go of the distant past. Just be hey, now, floating among the stars. Breathe slowly. Feel the weight of your body. You are here, on Earth, in the solar system, in the Orion Arm, in the Milky Way, part of something vast and ancient, part of the cosmos. Rest now. Rest. Neutron stars, dense remnants. Let's talk about something even stranger than white dwarfs. Neutron stars. These are the remains of more massive stars. Stars that were at least 8 times heavier than our sun. When such a star runs out of fuel, it doesn't gently shed its layers like the sun will. Instead, it collapses catastrophically. The core implodes in a fraction of a second. Then it rebounds. The outer layers explode outward in a supernova, one of the most violent events in the universe. What's left is the core, crushed to incredible density. A neutron star, Neutron stars are small, only about 20 kilometers across, about the size of a city, but they contain more mass than the Sun. Imagine that. A star's worth of matter compressed into a sphere the size of a city. The density is almost unimaginable. A teaspoon of neutron star material would weigh about 1 billion tons. 1 billion. If you could bring that teaspoon to Earth, it would instantly sink through the ground. Through the Earth. Nothing could support its weight. Neutron stars are made mostly of neutrons. The protons and electrons have been squeezed together so tightly they've merged. Only neutrons remain, packed shoulder to shoulder. The gravity on a neutron star is immense. If you could stand on the surface, you'd weigh billions of times more than on Earth. Of course, you couldn't stand. You'd be instantly crushed, flattened to less than the width of an atom. Pulsars, spinning lighthouses. Many neutron stars are pulsars. These are neutron stars that spin rapidly and emit beams of radiation from their magnetic poles. When a star collapses to form a neutron star, it spins faster. This is because of conservation of angular momentum. Like a figure skater pulling in their arms during a spin, the skater spins faster. The same happens with collapsing stars. Some neutron stars spin hundreds of times per second. Hundreds. Every second. These are called millisecond pulsars. As the neutron star spins, beams of radio waves shoot out from its magnetic poles. If one of those beams points toward Earth, we see a pulse. Then as the star rotates, the beam sweeps away. We see darkness. Then another pulse. And another. It's like a lighthouse. Spinning. Flashing. Pulsars are the lighthouses of the cosmos. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell. She was a graduate student at the time. She noticed regular pulses in her radio telescope data. At first, she wondered if it might be a signal from aliens. They even jokingly called it LGM1, Little Green Men 1. But soon they realized it was a natural phenomenon, a spinning neutron star. Since then, we've discovered thousands of pulsars. The nearest known pulsar to Earth is PSRJ 0108-1431. It's about 424 light-years away. Not exactly in our immediate neighborhood, but relatively close in cosmic terms. Pulsars are incredibly precise. Their pulses arrive with clockwork regularity. Some pulsars are more accurate than atomic clocks. Astronomers use them for timing experiments, for testing theories of gravity, for searching for gravitational waves. Supernova remnants. When a massive star explodes, it leaves more than just a neutron star. It also creates a supernova remnant, an expanding shell of gas. The outer layers of the star, blown into space. These remnants glow, heated by the shock wave, energized by radiation. They expand for thousands of years. Eventually, they fade and merge with the interstellar medium. But for a time, they are spectacular. The Crab Nebula is a famous supernova remnant. It's about 6,500 light-years away. Chinese astronomers recorded the supernova in 1054 CE. They said a new star appeared in the sky, so bright you could see it during the day. At the center of the Crab Nebula is a pulsar. The Crab pulsar. It spins about 30 times per second. Its energy powers the nebula, making it glow, making it pulse in optical light, radio waves, X-rays. Closer to home, we have remnants from ancient supernovae. The Vela supernova remnant is about 815 light-years away. It exploded about 11,000 years ago. Early humans would have seen it. A brilliant new star in the sky, brighter than anything except the sun and moon. These remnants are laboratories for physics, places where matter is accelerated to extreme speeds, where magnetic fields twist and tangle, where cosmic rays are born, and they are beautiful, filaments of glowing gas, shells and bubbles, colors from different elements, red hydrogen, green oxygen, blue sulfur. Each supernova paints a unique portrait in the sky. Star clusters, families of stars. Stars are often born in groups, hundreds or thousands of stars forming together from the same cloud of gas. We call these groups star clusters. There are two main types: open clusters and globular clusters. Open clusters are loose groups, maybe a few hundred stars. They are found in the disk of the galaxy. Young clusters contain hot, bright stars, blue and white. These stars live fast and die young, so open clusters don't last forever. Over time, the stars drift apart. The cluster dissolves. The Pleiades is a famous open cluster. You can see it with your eyes. A small group of bright stars. Some people call it the Seven Sisters. Through binoculars or telescope, you can see dozens of stars. The Pleiades is about 444 light-years away. The stars are young, only about 100 million years old. Another nearby open cluster is the Hyades. It's in the constellation Taurus. The Hyades is older than the Pleiades, about 625 million years, and closer, only about 153 light-years away. Our sun was probably born in an open cluster, along with thousands of siblings, but that was more than 4 billion years ago. The cluster has long since dissolved. The sun's siblings have drifted across the galaxy. We may never know which stars they are. Globular clusters are different. They are dense balls of stars, tens of thousands, sometimes hundreds of thousands, all packed tightly together. Globular clusters orbit in the halo of the galaxy, above and below the disk. They are old, very old, almost as old as the galaxy itself. The stars are ancient red dwarfs and red giants. Population 2 stars. The nearest globular cluster to Earth is NGC 6397. It's about 7,800 light-years away. Not exactly nearby. Globular clusters don't exist in our local neighborhood. They are all much farther out. But they are worth mentioning because they tell us about the history of the galaxy, about how it formed, about the first generations of stars. Looking at a globular cluster is like looking back in time, to when the galaxy was young. Variable stars, stars that change. Not all stars shine with constant brightness. Some vary, growing brighter, growing dimmer. These are called variable stars. Some vary because they are actually two stars eclipsing each other. These are called eclipsing binaries. When one star passes in front of the other, the brightness drops. Then it rises again, regular as clockwork. Other stars vary because they physically pulsate. They swell and shrink, like a beating heart. Cepheid variables are one type of pulsating star. They are supergiants, very large and very bright. As they pulsate, their brightness changes in a regular cycle. Some Cepheid pulse every few days, others every few weeks. The amazing thing about Cepheids is that their period of pulsation is related to their true brightness. The longer the period, the brighter the star. This makes them incredibly useful. If you know a star's true brightness and you measure its apparent brightness, you can calculate its distance. Cepheids are like cosmic measuring sticks. Astronomers have used them to measure distances across the galaxy and beyond. Another type of variable is the Mira variable, named after the star Mira. These are old red giants. They pulsate slowly, over months or even years. Some become so dim you can't see them with your eyes. Then they brighten again. Mira itself is about 300 light-years away. It varies in brightness over about 332 days. At its brightest, you can easily see it. At its dimmest, you need a telescope. And then there are irregular variables, stars that change brightness unpredictably. Often these are young stars, still settling down, still finding their equilibrium. Variable stars remind us that the universe is not static. Stars are active, dynamic, always changing, even on timescales we can observe in a human lifetime. The interstellar medium. Let's return to the space between stars. The interstellar medium. We've talked about gas and dust, but let's go deeper. The interstellar medium is complex. It has different phases, different temperatures and densities. The coldest regions are molecular clouds. The temperature is only about 10 to 20 degrees above absolute zero. Absolute zero is the coldest possible temperature, the point where atoms stop moving. Molecular clouds don't quite reach that, but they are close. In molecular clouds, atoms have combined to form molecules. Hydrogen molecules, water molecules, carbon monoxide, ammonia, even more complex molecules, amino acids, the building blocks of life. These clouds are where stars are born. Gravity slowly pulls the gas together. Dense cores form. Eventually, fusion ignites. A star is born. Warmer regions are called HII regions. Radiation from hot young stars has ionized the hydrogen, stripped away the electrons. The gas glows red, like a neon sign. The Orion Nebula is an HII region. So is the Lagoon Nebula. So is the Eagle Nebula with its famous pillars of creation, all glowing with the light of ionized hydrogen. Then there's warm ionized medium, diffuse gas filling much of the galaxy, heated by starlight and supernova shocks, glowing faintly, and hot ionized medium, gas heated to millions of degrees by supernovae. This gas fills bubbles and superbubbles. It's invisible to optical telescopes, but X-ray telescopes can see it glowing. All these phases coexist, mixing, interacting. Gas flows from one phase to another, cooling, heating, condensing into stars, exploding back into space. The interstellar medium is a cosmic ecosystem. Energy flows through it. Matter cycles through it. Stars are born from it and return to it. It's the connective tissue of the galaxy. Without the interstellar medium, there would be no new stars, no planets, no life. We owe our existence to this thin gas, this dust, this seemingly empty space between the stars. Magnetic fields in space. Space is filled with magnetic fields, invisible lines of force threading through the galaxy. Stars have magnetic fields. The sun's magnetic field creates sunspots and flares. Neutron stars have even stronger fields. Magnetars, a type of neutron star, have the strongest magnetic fields in the universe. Strong enough to distort atoms. Strong enough to be dangerous even from thousands of kilometers away. The galaxy itself has a magnetic field. It follows the spiral arms, threading through the disk. The field is weak, much weaker than Earth's magnetic field, but it's there. Magnetic fields affect the interstellar medium. They provide pressure, support. They guide the motion of charged particles. Cosmic rays spiral along magnetic field lines. Magnetic fields also affect star formation. They can resist gravity, making it harder for gas clouds to collapse. But they can also help, channeling gas, creating dense filaments where stars can form. We can't see magnetic fields directly, but we can detect them by measuring how they affect light, by observing the motion of charged particles, by studying radio waves emitted from energetic electrons spiraling in the fields. Magnetic fields are a hidden architecture of the galaxy, a scaffolding that shapes the visible structure. They are part of the invisible universe, the dark framework supporting everything we see. Rest now. Let these ideas wash over you. Magnetic fields, interstellar medium, variable stars, clusters and remnants, all parts of our local neighborhood, all parts of the cosmic tapestry. You don't need to remember every detail. Just feel the vastness, the complexity, the beauty. Breathe, relax, float among the stars. Stellar nurseries. Let's visit where stars are born. The stellar nurseries of our neighborhood. Places where gas and dust collapse to create new suns. The nearest major star-forming region is the Taurus molecular cloud. It's about 430 light-years away. A vast complex of dark clouds, cold and dense, hiding from view behind veils of dust. But infrared telescopes can peer through the dust. They reveal what's happening inside. Young stars, protostars, still gathering mass, still growing. Some of these young stars are surrounded by disks, protoplanetary disks, made of gas and dust. This is where planets form. Dust grains stick together, growing larger. Pebbles, boulders, mountains, eventually, planets. We can see these disks around many young stars. Flat circles of material. Some have gaps in them, carved by newly formed planets. These gaps are like footprints, evidence of planets we can't see directly. The youngest stars are still embedded in their birth clouds, cocooned in gas and dust. They flicker and vary, surrounded by infalling material. These are called protostars. Not quite stars yet, but getting there. As a protostar gathers mass, it heats up. Eventually, the core becomes hot enough for fusion to begin. Deuterium fusion first. Then, if the mass is sufficient, hydrogen fusion, the star turns on. It begins to shine. The energy from the young star pushes back against the infalling gas. Eventually, it clears away the cocoon. The star emerges, visible at last. A T-Tauri star, young, active, still surrounded by its protoplanetary disk. T-Tauri stars are named after the first one discovered, in the constellation Taurus. They are a few million years old, still babies by stellar standards. They are variable, sometimes flaring, sometimes dimming, restless and energetic. Over time, the disk disappears. Some material falls into the star. Some is blown away by stellar wind. Some becomes planets. After about 10 million years, a young star system is complete. A star, planets, moons, ready to settle into a long, stable life. The Orion molecular cloud. The most famous star nursery near us is the Orion molecular cloud, about 1,300 light-years away. A giant complex, one of the most active star-forming regions within a few thousand light-years. At the heart of the cloud is the Orion Nebula. You can see it with your eyes on a dark night. A fuzzy patch in Orion's sword. Through a telescope, it's breathtaking. The Orion Nebula is an HII region, ionized by a group of hot young stars called the trapezium. 4 bright stars, easy to see through a small telescope, but actually a small cluster of more than 1,000 stars. These stars are young, only about 1 or 2 million years old. They formed recently from the same cloud. They are massive and hot, bright blue-white, pouring out ultraviolet radiation. This radiation ionizes the surrounding gas, making it glow. Behind the visible nebula lies a larger, darker cloud, the Orion Molecular Cloud Complex. This is where star formation is still happening, hidden from visible light. But infrared telescopes reveal hundreds of protostars embedded in the cloud, growing, warming, getting ready to emerge. The Orion Nebula also contains structures called proplyds, protoplanetary disks, silhouettes against the bright nebula, dark teardrops of dust and gas, each one a potential solar system, planets forming around a young star. Looking at the Orion Nebula is like looking at a younger version of our own solar system. This is what the Sun looked like 4.5 billion years ago. A young star in a nebula, surrounded by a disk, just beginning its long journey through the galaxy. Herbig-Haro objects. Star formation is violent. It doesn't happen quietly. Young stars send out jets of material, fast streams of gas shooting out from their poles. These jets crash into the surrounding cloud. The collisions create shock waves, glowing knots of gas. We call them Herbig-Haro objects, named after George Herbig and Guillermo Haro, 2 astronomers who studied them in the 1950s. Herbig-Haro objects are beautiful, small glowing clouds, often in pairs. 1 jet on each side of the young star. They change over time, moving, fading, new ones appearing. They are evidence of the struggle between a young star and its environment. The star is trying to clear space around itself, pushing back against the infalling gas, creating these luminous markers of its birth. Our Sun probably created Herbig-Haro objects when it was young. jets shooting out, colliding with the surrounding cloud. But that was so long ago. The cloud has long since dispersed. The jets have faded. No trace remains. Red dwarfs and their longevity. Let's return to red dwarfs. We've mentioned them before. The most common type of star. Small, cool, dim, but there's something remarkable about them. Red dwarfs live for a very long time. The smallest ones burn their fuel so slowly they can last for trillions of years. Trillions. The universe is only about 13.8 billion years old. Not even 1/100th of a trillion. This means every red dwarf that has ever formed is still alive. None have reached the end of their lives yet. They are all still burning, still shining, still waiting. Eventually, trillions of years from now, the first red dwarfs will begin to die. They'll exhaust their hydrogen. They'll cool and fade, becoming white dwarfs. But that's so far in the future it's almost meaningless. In a way, red dwarfs are the future of the galaxy. Long after stars like the Sun have died, long after massive stars have exploded, red dwarfs will remain. The last stars shining in an aging galaxy. Planets around red dwarfs might be the most common type of planet, and some are in the habitable zone, close to the star, receiving just enough warmth for liquid water. Life on such planets would experience a different kind of time. The star would be steady, unchanging for billions upon billions of years. No aging sun to worry about. No red giant phase to escape. Just endless stability. Of course, there are challenges. Red dwarfs produce flares. Strong flares that could harm life. And planets in the habitable zone are tidally locked. One side always facing the star. One side always dark. But life is adaptable. If it can exist, it finds a way. Perhaps red dwarf planets are full of life. Patient life. Slow life. Adapted to the dim red light and the endless day on one side. The endless night on the other. The motion of the sun. Our sun is not standing still. It's moving through space. Orbiting the galaxy. But also moving relative to nearby stars. The sun is traveling toward a point in the constellation Hercules. We call this the solar apex, the direction we're heading, at about 20 kilometers per second relative to nearby stars. The opposite direction, where we're coming from, is called the solar antepex. It's in the constellation Columba. This motion is slow by cosmic standards, but over long periods, it adds up. The sun drifts through different neighborhoods, different stellar populations. About 70,000 years ago, a red dwarf called Scholz's star passed close to the sun. It came within about 0.8 light years. That's very close. Almost into the outer reaches of the Oort cloud, the distant shell of comets surrounding the solar system. Scholz's star didn't cause any problems. It's too small, too dim, but it's a reminder that space is not empty. Stars pass by, not often, but it happens. In about 1.4 million years, the star Gliese 710 will pass even closer, only about 0.2 light years. It might disturb comets in the Oort cloud, sending some of them toward the inner solar system. Potential comet showers for Earth, but that's far in the future. For now, we're in a quiet part of space. No close encounters coming soon. just the slow, steady orbit around the galaxy. The galactic orbit. The Sun takes about 225 to 250 million years to orbit the galaxy once. This is called a galactic year, or cosmic year. Since the Sun formed, it has completed only about 20 galactic orbits. 20 trips around the galaxy. That's all. In cosmic terms, the Sun is still getting to know its home. During these orbits, the Sun moves up and down through the galactic disk. Right now, we're near the midplane, the center of the disk, but we oscillate. Every 30 million years or so, we pass through the midplane. Then we move above it, then below it, then back through again. Some scientists have wondered if this oscillation affects Earth. When we pass through the midplane, we're in a denser part of the galaxy. More stars, more dust, perhaps more comet impacts, perhaps mass extinctions. It's an interesting idea, but the evidence is not clear. There might be a weak correlation, or there might not. The data is noisy. The galaxy is complex. It's hard to untangle cause and effect. What's certain is that the Sun's path through the galaxy is not simple. We're not just circling the center. We're bobbing up and down, drifting inward and outward, encountering different environments, different stellar populations. The Orion Arm is our current home, but millions of years ago, we were somewhere else. And millions of years from now, we'll be somewhere else again. The Sun is a traveler, and we travel with it. The night sky changes. The stars we see at night are not fixed. They move, slowly, over centuries and millennia. The constellations change shape. The ancient Greeks saw different constellations than we do. Not completely different, but subtly altered. Stars have shifted position. Some have brightened, some have dimmed. In 10,000 years, the Big Dipper will look different. The handle will bend. The bowl will stretch. It will still be recognizable, but changed. In 100,000 years, most constellations will be unrecognizable. The stars will have drifted too far. New patterns will emerge. Future humans, if they exist, will join new constellations, tell new stories. This is called proper motion, the apparent movement of stars across the sky. It's caused by the real motion of stars through space, combined with our own motion. Barnard's star, remember, has the largest proper motion. It moves noticeably over just a few years. But most stars move much more slowly. Their motion is measured in tiny fractions of a degree per year. Still, over long enough periods, everything changes. The sky is not eternal. It's a snapshot, a moment in the galaxy's long evolution. Our ancestors looked up at different skies. Our descendants will look up at different skies still. But all will see stars. All will wonder. All will feel the same sense of or in connection to the cosmos. Exoplanets in our neighborhood. We've talked about stars. But what about planets? Planets around other stars. Exoplanets. Thousands of exoplanets have been discovered. Many are nearby, within a few dozen light years. Proxima b, as we mentioned, is the closest, only 4.2 light years away. A rocky planet, possibly habitable. Then there's Epsilon Eridani, a star about 10.5 light years away. It has at least one planet, a gas giant, maybe more. It also has 2 asteroid belts, and possibly a planetary system similar to ours. Tau Ceti is about 12 light-years away. It might have several planets, some in the habitable zone. Tau Ceti is similar to the Sun, slightly smaller, slightly cooler, but close enough that it's been a target in the search for extraterrestrial intelligence. TRAPPIST-1 is about 40 light-years away, a red dwarf, but a special one. It has 7 planets. 7, all about the size of Earth. 3 or 4 in the habitable zone. It's one of the most exciting planetary systems we've found. Imagine that. 7 Earth-sized worlds, orbiting close together. So close that if you stood on one, you could see the others in the sky. Not as points of light like we see planets, but as disks, crescents, maybe even continents and clouds if you had a good telescope. Life on TRAPPIST-1 planets would be strange. The star is dim. The planets are close, tightly locked, always one side facing the star. But the planets might have atmospheres, wind, weather, perhaps even life. These are just a few examples. There are many more exoplanets in our neighborhood. Every year we find more. Small ones, large ones, hot ones, cold ones, rocky ones, gaseous ones. The galaxy is full of planets. More planets than stars, probably. And many are right nearby, in our local neighborhood, silently orbiting their stars, waiting, perhaps some with life, perhaps some with civilizations. We don't know yet, but we're looking. Rest now. Think about those distant worlds, orbiting distant suns. Some might have oceans, some might have mountains, some might have beings looking up at their own night sky, wondering if they're alone. Just as we wonder, you are part of this cosmic community, even if separated by vast distances, even if we never meet. We share the same galaxy, the same laws of physics, the same stardust origins. Breathe, relax, be at peace. The cosmic distance ladder. Let's talk about how we measure distances in space. It's not easy. You can't stretch a tape measure to the stars. For nearby stars, we use parallax. As Earth orbits the Sun, nearby stars appear to shift position against more distant stars. It's like when you hold your finger in front of your face and close one eye, then the other. Your finger appears to jump. The closer the star, the bigger the shift. By measuring this shift, we can calculate distance. This method works for stars within a few hundred light years. For more distant stars, we use other methods. Standard candles, objects with known brightness. If you know how bright something truly is, and you measure how bright it appears, you can calculate its distance. Cepheid variables are standard candles. So are certain types of supernovae. Type Ia supernovae. These happen when a white dwarf reaches a critical mass and explodes. They all explode with roughly the same brightness. So they make excellent distance markers. Each method builds on the previous one. Like rungs on a ladder, we call it the cosmic distance ladder, starting with parallax for nearby stars, then using those stars to calibrate Cepheids, then using Cepheids to calibrate supernovae, then using supernovae to measure distances across the universe. It's a delicate chain. Each link depends on the previous one. If there's an error early on, it propagates through the whole ladder. Astronomers work carefully, constantly refining, constantly checking. Distance is fundamental to understanding the universe. If you don't know how far away something is, you can't know how big it is, how bright it is, how massive it is. Distance is the key that unlocks everything else. The habitable zone. We've mentioned the habitable zone several times. Let's explore it more deeply. The habitable zone is the region around a star where temperatures allow liquid water to exist on a planet's surface. Not too hot, not too cold, just right. We sometimes call it the Goldilocks zone. For stars like the Sun, the habitable zone is roughly where Earth is, from about 0.9 to 1.5 astronomical units. An astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. Venus is too close, too hot. Water boiled away long ago. Mars is on the outer edge, mostly too cold. Water is frozen, though in the distant past, Mars might have been warmer, with liquid water on its surface. For red dwarfs, the habitable zone is much closer. The star is cooler, dimmer. Planets need to huddle close to receive enough warmth. Sometimes they orbit in just days or weeks. For hotter stars, bigger stars, the habitable zone is farther out. These stars are bright. They pump out enormous energy. Planets need to keep their distance to avoid being scorched. But the habitable zone is just an estimate. It depends on many factors. A planet's atmosphere, its greenhouse effect, whether it is oceans, clouds, volcanism, plate tectonics. Venus is technically in the Sun's habitable zone, but a runaway greenhouse effect turned it into a hellscape. Surface temperature is hot enough to melt lead. Mars is at the edge. Too cold, but if it had a thicker atmosphere, it might be warmer, more hospitable. Even planets outside the habitable zone might harbor life. Europa, a moon of Jupiter, has an ocean beneath its icy shell, heated by tidal forces, not by sunlight. Life might exist there, in the dark, in the deep, so the habitable zone is a guide. A starting point, not a rule. Life might be more flexible than we imagine, more creative, more resilient. The Drake equation. Are we alone in the universe? It's one of the biggest questions, one humans have asked for millennia. In 1961, astronomer Frank Drake proposed an equation, a way to estimate the number of communicating civilizations in the galaxy. We call it the Drake equation. It breaks the problem into factors: the rate of star formation, the fraction of stars with planets, the number of planets in the habitable zone, the fraction where life develops, the fraction where intelligent life develops, the fraction that develops technology, and how long such civilizations last. Multiply all these factors together, and you get an estimate. But here's the problem. We don't know most of these numbers. We can guess. We can estimate. But we can't be sure. We know stars form. We know most stars have planets. Thanks to missions like Kepler, we know rocky planets in habitable zones are common. But we don't know how often life develops. We have a sample size of one, Earth. And even on Earth, life took a long time to become complex. Simple cells existed for billions of years. Multicellular life is recent. Intelligence is very recent. Technology is brand new. Just a blink in cosmic time. Some scientists think life is common. Given the right conditions, it emerges readily. Others think it's rare, a fluke. a 1 in a billion chance. And even if intelligent life is common, technology might be rare or short-lived. Civilizations might destroy themselves, or lose interest in communication, or exist but remain undetectable. The Drake equation doesn't give us an answer. It gives us a framework, a way to think about the question. And as we learn more, we fill in the numbers. The equation becomes less speculative, more grounded in data. The Fermi paradox. Related to the Drake equation is the Fermi paradox, named after physicist Enrico Fermi. The paradox goes like this. The galaxy is old, about 13 billion years. Stars have been forming for most of that time. There's been plenty of time for intelligent life to develop, to spread, to colonize the galaxy. Even with slow spacecraft, traveling at a fraction of the speed of light, a civilization could spread across the entire galaxy in just a few million years. A blink of an eye in cosmic terms. So where is everyone? Where are the aliens? Why don't we see evidence of them? No megastructures, no radio signals, no probes visiting our solar system. Fermi supposedly asked this question casually over lunch. Where is everybody? It's become one of the most famous questions in science. There are many proposed answers. Maybe life is rare. Maybe intelligence is rare. Maybe technological civilizations don't last long. Maybe they destroy themselves. Nuclear war, climate change, artificial intelligence gone wrong. Maybe they are out there, but we're not looking in the right way. Maybe they use communication methods we haven't thought of. Maybe they're deliberately hiding. Maybe they are ignoring us. Maybe we're not interesting enough. Or maybe we're the first, the earliest civilization in the galaxy. Someone has to be first. Maybe it's us. We don't know. The silence is mysterious, unsettling, or perhaps comforting, depending on your perspective. But the search continues. SETI, the search for extraterrestrial intelligence, listening for signals, watching for anomalies. Maybe one day, we'll detect something, a pattern in the noise, a message from the stars. Or maybe we won't. Maybe we're truly alone. Or maybe the galaxy is full of silent civilizations, all listening, none broadcasting, all afraid, or cautious, or simply content in their solitude. The speed of light barrier. Space is vast. Even our local neighborhood is enormous. And the speed of light, fast as it is, feels slow on cosmic scales. Light travels at about 300,000 kilometers per second. Nothing can go faster. It's a fundamental limit, built into the structure of space-time itself. At light speed, you could circle Earth 7.5 times in 1 second. You could reach the moon in about 1 second, the sun in 8 minutes, Neptune in 4 hours. But reaching even the nearest star would take over 4 years. Alpha Centauri, just next door, 4 years at light speed. And we can't travel at light speed. Not even close. The fastest spacecraft humans have built, the Parker Solar Probe, travels at about 190 kilometers per second at its peak. That's fast. But it's only 0.06% the speed of light. At that speed, it would take about 7,000 years to reach Alpha Centauri. 7,000 years. Longer than recorded human history. This is the Great Barrier, the challenge of interstellar travel. Space is too big. Light is too slow. Or we are too slow. Take your pick. Science fiction often invents faster-than-light travel. Warp drives, wormholes, hyperspace. These make for exciting stories, but physics, as we understand it, doesn't allow them. Maybe one day we'll discover new physics, new loopholes, ways to cheat the light speed limit. Or maybe not. Maybe we're stuck, bound to our local corner of the galaxy. But that's okay. Our local neighborhood is vast, full of wonders. Thousands of stars within a few dozen light years. Tens of thousands within 100. We have plenty to explore, even if we never leave our little bubble. Generation ships and the long journey. If we can't travel faster than light, and even a significant fraction of light speed is beyond us, how could we ever reach the stars? One idea is generation ships, massive spacecraft, self-contained ecosystems, carrying thousands of people, traveling for centuries or millennia. The people who launch wouldn't arrive, nor would their children, nor their grandchildren. Many generations would live and die aboard the ship. Only their distant descendants would see the destination. It's a daunting prospect. Can humans remain stable and functional across so many generations? Can we maintain technology, prevent conflict, keep hope alive? Would people born on the ship even want to reach the destination? The ship would be their home, their world. The destination just an abstract idea, a story told by their ancestors. Another idea is suspended animation. Freeze the crew, or put them in a deep sleep. Wake them when you arrive. This appears often in fiction, but the biology is challenging. Can human bodies survive being frozen? Can they be revived? We don't know yet. Or perhaps we send robots, artificial intelligence. Let them explore the stars on our behalf. Send back data, build outposts, maybe even prepare worlds for eventual human arrival. Or maybe we never go ourselves. Maybe we're content to observe from afar, to listen, to watch, to study. The universe is vast. We can learn much without leaving home. For now, we remain on Earth, orbiting our sun, in our local neighborhood, looking out at the stars, dreaming, wondering, planning. Maybe one day we'll take the leap. Or maybe we'll stay here. Either way, the stars will continue to shine, waiting, patient, eternal. The ancient light. When you look at the stars, you're looking into the past. Light takes time to travel, even at its immense speed. Crossing cosmic distances requires time. The light from the sun is 8 minutes old. When you see the sun, you're seeing it as it was 8 minutes ago. If the sun suddenly vanished, you wouldn't know for 8 minutes. The light would keep coming. The Earth would keep orbiting. For 8 minutes, nothing would seem wrong. The light from Alpha Centauri is 4 years old. When you look at it, you see it as it was 4 years ago. It might have changed. It might have exploded. You wouldn't know yet. Sirius, 8.5 years ago. Vega, 25 years ago. Every star you see is a messenger from the past. The farther away, the older the message. Some stars you see might already be dead, exploded as supernovae, but their light hasn't reached us yet. For now, they still shine in our sky. Ghosts, echoes. When you look at distant galaxies, you see them as they were millions or billions of years ago. You're not seeing the present universe. You're seeing its history. This is one of the strange beauties of astronomy. We can look back in time, just by looking far away. The universe is its own time machine, but it also means we can never see the universe as it is now, only as it was. The present is always hidden, always out of reach. We live in our own tiny bubble of now. surrounded by the past. So when you look up at the night sky, remember, you're not seeing the present, you're seeing history, ancient light, traveling for years, for centuries, for millennia, finally reaching your eyes, completing its journey, telling you stories from long ago and far away. Close your eyes now, or keep them open, looking at the stars in your mind. Each one a beacon, each one a history, each one a sun, maybe with planets, maybe with life, all part of our galaxy, our home, our local neighborhood in the vast cosmos. You are here, now, in this moment, but connected to all of it, to the stars, to the past, to the future, made of the same atoms, following the same laws, part of the same grand story. Let that thought fill you, comfort you, let yourself drift into sleep, into dreams, into the peaceful dark. Rest well, traveler, rest well.